Okay, is my voice clear?
Yeah, you're coming through great.
Okay. Hello, everyone. I'm Dacheng from Tsinghua University. Today, my topic is a survey of PMT waveform analysis methods. Okay, in motivation part, first, I would like to give a really quick reminder of Jinping neutrino experiment where I'm working at. Jinping neutrino experiment is located at China Jinping Underground Laboratory in the interior of China, as the asterisk shows in map. The CJPL has an overburden of 2,400 meters, which provides an extremely low cosmic muon flux. Additionally, CJPL is far from nuclear reactor, which provides a low reactor neutrino flux. So the CJPL is an ideal site of low background physical research. And there's an ongoing 1-ton prototype in CJPL. And next, we will build a 100 tons magnitude detector for Jinping neutrino experiment. And in future, we'll build an 5,000 tons detector. And we need to study the neutrino-involved interaction to understand the property of neutrinos. A lot of interaction can be revealed by light glowed from the liquid scintillator. And we need to record the time and amount of photons which hit the PMTs, which shows here. And the time resolution is crucial in neutrino event reconstruction. So the question is how we can improve it. The time resolution is determined by the PMT and waveform analysis. The typical PMT response includes 3 individual processes. The first one is the photon-electron conversion happened on the photon cathode and electron collection by the first dynode. And the third one is amplification of electrons between the dynodes. So one photon incoming has a certain probability to be observed via the PMT response, as shown on the left. But if photons hit the PMT continuously, the PE response will pile up, and the waveform analysis will be difficult, as the figure shows here. So the pile up will significantly worsen the timing resolution. So how we solve this problem? Naively, when we handle PMT waveform, we will record the first hit time according to the threshold and the integration of waveform. So one waveform is converted to a pair of numbers, and we lose some detailed information of the waveform. So our new goal is to extract all detailed information in one waveform. The information we extracted includes a sequence of hit time and charge, or the P number. The charge is the integration of waveform components, which induced by one photon electron. And single PE induced charge can be a wide distribution, as shown on the figure right here, rather than a single value. So reconstructing P number or the photon electron number is more difficult than reconstructing the charge. So first of all, how we define the difference or the distance between the reconstruction result and the truth properly. We import the Wasserstein distance. For most familiar distance is listed here, but the shortcoming of them is obvious. They cannot compare the discrete distribution with continuous distribution, and they are not sensitive to timing. As the graph shows here, the L2 distance between AB1 and AB2 is both 0.25, but the B1 and B2 distribution looks really different. So what is Wasserstein distance? We can understand Wasserstein distance between mu and nu as the minimum effort to transport mass from the distribution mu and nu. And we can understand that the further the mass moves, more the effort we need to give. So we can imagine that the effort is controlled by the plan about how we transport the mass. And the transport plan is described by pi AB. As the figure shows, delta W is the sum of mass and path length product. And then we integral A and B. We will get a distance corresponding to the plan pi AB. And when we choose the best transport plan in the plan space, which the capital pi here, to minimize the effort, we get the Wasserstein distance. And in practice, the loss we use in numerical calculation is defined here, the dW. The CDF here means the cumulative distribution function. We first calculate the subtraction of the CDF A and CDF of B, which shows here. Then take the sum of absolute value of the subtraction. That is the area plotted in the dark blue. And that is the L1 distance of cumulative distribution function of A and B. We can prove that the distance we define here is equivalent to the Wasserstein distance. Okay, and before taking deep look into all the methods, we need to define input and output. The input is a pedestal subtracted PMT waveform, as shown here. And the output is a charge or P number sequence, as shown here. And the loss we use is a Wasserstein distance between reconstructed result and the truth. Total photon electron number is the count of heat time. The heat time is the third column here. And here is a histogram of total electron, total photon electron number and the data structure. Okay, and first intuitive method is find peak method. First, we find the peak of the waveform. The black arrow shows here. And then we move them leftward. The delta T we move is the peak time of a single P response. And the average delta Wasserstein distance is approximately 11 for charge and P number. And the next one is waveform shift method. And first, we locate the part of waveform exceeds the threshold. And then we shift the exceeding part leftward and treat the normalized exceeding part as charge or P number. The average Wasserstein distance is approximately 3 to 4 for charge and P number. And the third one is Fourier deconvolution. We can assume that the waveform is the convolution of single P response and the heat time sequence. So we compute the FFT of waveform and the single P response, and we add a rectangular filter to the FFT of the waveform. And then compute the inverse waveform, inverse FFT of the quotient of filtered FFT of waveform and FFT of single P response. And the Wasserstein distance is shown here. And next is Lucy deconvolution. Lucy-Richardson deconvolution is a nonlinear iteration method to calculate the deconvolution of signals. Lucy deconvolution has an advantage against the FFT just mentioned. The Lucy deconvolution has a constraint that the charge of all P number are larger than 0. The average Wasserstein distance for charge is 0.93, and for P number is 2.774. Okay, we also developed a convolutional neural network to analyze the waveform. And here is the structure of the CNN, which has 5 convolutional layers. And the length of data remains the same as the figure shows here. And in the training process, we train the CNN for each PMT channel. And here's the loss, which is Wasserstein distance during the training. It's downward to the approximately 1.2. And the results shows that CNN is the best for reconstruction of PE number. And here is the histogram. The average Wasserstein distance for P number is 0.76, and for charge is 2.25. And here's the statistical graph for the CNN result. As shown here, the blue line is the Wasserstein median, and minus and plus the MAD. And the green line is here is the Wasserstein mean, and plus and minus the standard deviation. And the last method is fitting, also known as matching pursuit. First, we extract enough single P response from the simulation data. We suppose the average of these waveform is the single P response. In fitting process, the parameter is weight in each discrete hit time. The loss which we need to optimize is the truth waveform and the reconstructed waveform according to the parameters. And the graph here shows one of the fitting results, which has a Wasserstein distance of 1.51. And the fitting method is best for construction of charge. And here's a histogram. And the average Wasserstein distance is 0.54 for charge and 2.46 for the P number. And here is the statistical graph for the fitting method. Okay, now we can give a summary of these methods. And the first one is the reconstruction of charge. The error bar shows here is 10 to 90 percentile of the Wasserstein distance. And the best here is the fitting one. Just like I mentioned, it has 0.56 of Wasserstein distance. And next one is a summary of reconstruction of P number. The best one here is the CNN method. It has 0.76 of Wasserstein distance. And we also tested the efficiency of all methods. And here's the efficiency of CNN fitting and Lucy deconvolution method. And the CNN is faster than Lucy deconvolution and much faster than fitting. And the GPU and CPU we use are shown here. Okay, in the summary part, we can say that the fitting method is the best for reconstruction of charge, while the Lucy deconvolution looks promising. And the CNN method is the best for reconstruction of the number of PE. And it is also the fastest. We developed several representative methods to extract photon timing information hidden in the PMT waveforms. And these methods will improve the precision of event reconstruction and particle identification. And we are working on applying these methods on analyzing the real data. Okay, and here's the acknowledgement. Okay, my part is over here.
Yay. Nice. We have a few questions if we have a little time. I know we're a little over on time.
That's fine. We can go until the break at 9:10. Okay.
So first question, how fast does fitting need to be? Just curious if this can run live.
I think,
Dacheng, do you want to share the questions? You can just maximize that. You probably want to share in case you.
Okay, I'll share the website.
That question, I accidentally deleted it. That's my mistake. Here, I can put
I restored
it
it.
Oh, I did it too. So.
Okay.
And move that to the top. There it is.
Yes, I think the fitting method here is rather slow, and we are working at it. It is not practical now. We are working at the improve of the speed.
But how fast does it need to be for the detector? That probably sets the speed, right? Your data acquisition rate.
Yes, because we analyze the data offline, so maybe the speed of the method is not a strict limit, because we can improve the cores of the CPUs. So if we have enough the calculation resource, we can improve it significantly. And I cannot. I must say I cannot give a accurate speed of the enough efficiency. Okay, and
next question is for the Wasserstein distance. This is just the distance between distributions. Why is that the best finding time?
Because we compare the reconstruction result to the truth. If the Wasserstein distance is 0, we can say that the reconstruction is perfect. I'm not sure I have answered that question.
Oh, I asked it. So I think you did. When you were talking, I thought that you that for some reason this metric was the best for finding times, but it's just a way of comparing two distributions. And if they agree perfectly, then the time is, I mean, the correct one. But it's not that this is something special.
Will be 0. Yes.
Yeah, I just was. I thought I might have missed something. But, okay.
Yes, and it is just a good distance for the difference of the reconstruction result and the truth. Okay, the next question maybe I need to refer on the slide 8. Okay. I think is a typical charge distribution model that includes Gaussian distribution and the Poisson distribution. Okay, and do you have a... Oh, that part is we're working at here. The systematic error is being tested.
May I answer this question? How well do you have to measure the times for science? I think it boils down to the vertex resolution for large liquid scintillator detectors. So if the detector is large, we have to rely on the time of flight measurement of photons. So this measure of time directly translates to vertex resolution. And the answer will be the better the resolution, the better we can do for science at this moment.
What, just since we all work on different experiments, what orders of magnitude are we talking about? Like what energy resolution, what position resolution, what time resolution are you hoping?
It's about like 1 MeV. at the vertex resolution of 10 centimeter scale. And the improvement of timing would directly translate into the distance, because it's proportional by the speed of light. And that's almost a linear improvement for vertex reconstruction.
Okay, I'll answer the next one. And it's not the raw waveform because the raw waveform includes the pedestal. We use some algorithm to subtract the pedestal and give that subtracted waveform into the CNN.
Thanks.
So I guess since we got all of the questions, now we're at coffee break time, or, well, depending on your time zone, whatever else you're up for. So we'll meet again in 20 minutes, where we'll have a mix of talks, including Lux and LZ.
10 minutes, Chris.
Oh, sorry, 10. Oops.
Yeah, this is a short one, and then we have a long break at 10:30.
Okay. Let me actually just load up the schedule. I'll just leave this. So see everyone in 10 then. Sorry about that. And yeah, so just remember, you can always post questions during people's talks, and we'll talk soon.